In this video, we're going to change our perspective on the types of problems that we're looking at. So previously, when we were calculating probabilities, we were always saying, we're going to do an experiment. What answer do we get? What's the probability of that happening? I'm going to roll a dice. What's the probability that I get a 3? I'm going to flip a coin 5 times. What's the probability that I get 2 heads? I'm going to do this. What's the chance of that happening? Now, instead of doing a single random experiment, whatever it may be, we are going to be taking samples from a population. And taking that sample, that is going to be our random experiment. And the reason why it's random is every time we're taking a sample, at least a random sample, the people that we get in that sample were a random choice. And so that means the data that we're going to get is random data based on those random people. And so when I calculate, in this case, the mean of that sample, I'm getting a random answer. Now, it's not completely random. It's going to depend on like the population. For example, if you're taking a height of adult men, you're not going to get an average height for a sample that is 15 feet tall. That's not possible because there aren't humans that are 15 feet tall. So when we take samples, it's not like the random answer can be just any number possible. It's going to be restricted based on the population information that you have. And so what we're going to study right now is what can we say about those random means? What can they be? What kind of distribution are they going to have? And then what probabilities can we say? So we could say, okay, it's true that the sample for your adult male height is not going to be over 15 feet, but maybe your average is over 6 feet. And how likely would it be for you to take a sample and get an average over 6 feet? Now, that's a different question than saying, what's the probability of a single adult man being over 6 foot tall? Now we're saying, what's the probability that you take a group of, say, 10 people and the average is over 6 foot tall? So we are going to be asking different questions now, and we need to study what's going to happen in this scenario. So let me kind of summarize it. Here's what happens if we take many samples and calculate the sample mean for each sample. So each sample is a random selection of individuals. And so the sample mean, x bar, is a random variable. And we're going to study the random variable x bar now, and we're going to see how can we calculate probabilities involving the x bar random variable. But before we even get to that, it turns out we can talk about the mean and standard deviation of the random variable x bar, and it's pretty straightforward. So if you take samples of size n, then the mean of all x bars from all possible samples is the same as the mean of the population. And we write that as saying the mean of the x bars is the same as the mean of the x. And I can kind of justify that really quickly here in that if you're taking samples from the population, then assuming it's a simple random sample, everything is equally likely to be chosen. And so every time you take a sample, every individual in the population has an equal chance of being picked. So they're all going to get counted equally in the average, which is the same thing as taking the average of all of the population. However, get back to my earlier question. If you think about taking a single individual and saying what's the chance of them being greater than 6 foot tall, and then the second question is if you take a group of 100 men and say what's the chance that the average height is over 6 foot tall, that's actually going to be a much smaller chance of that happening. Because even if you have some people more than 6 foot tall, having an average over 6 foot means you need a lot of tall people in your group, and that's a harder thing for that to happen. So what ends up happening is, even though the average is still the same, the variance, the standard deviation, is actually going to change here. And I can say the standard deviation is decreased by a factor of square root of n, and that means that the standard deviation of the x bars is the standard deviation from the original population divided by the square root of the sample size. So you need to understand that we are changing the standard deviation here. Even though the mean is still the same, the standard deviation is getting smaller based on the sample size. In other words, it's not hard for an individual to be, unusually tall or unusually short, but it's much rare for a group of people to all essentially be unusually tall or unusually short. Right? Sure, if you take a sample of basketball players, maybe you're going to get a really high average height, but that's not going to happen unless you do take a sample of like basketball players. So it's much less likely. Everything's going to get kind of more pushed together in the middle. The values of your samples are going to be closer to the actual average than individuals would be, rather than that. So we end up changing the standard deviation by dividing by square root of n, and you can prove that mathematically. And we're going to give this a name here. This is actually called the standard error of the mean. And this is going to come into play a little bit later, but for right now, we'll just call it the standard error of the mean. So really quickly, we now know that if we're taking a bunch of random samples and you're calculating the mean for each one of them, the x bar for each one of them, that's a random variable. And we now know the mean of that random variable is the same mu as the population. And the standard deviation of that random variable is the same as the standard deviation of the original population divided by root n. So now the question is what type of distribution are you going to have for this? Well, you might say, well, maybe it's binomial, right? We learned about binomial. We learned about uniform. We learned about skewed left and skewed right, but it turns out it's none of those things. The central limit theorem tells us the following, is that in every case, and this is maybe not perfectly true the way I'm saying it, but I'll leave it, let it slide here for this class. In every case, as you make n large enough, the values of x bars from the samples will have an approximate or approximately normal distribution. So that whole thing we learned about before called the normal distribution, here it's popping up again. So that means even if you start with something originally that is not normal, if you take big enough sample size though, the x bars are going to be normal. On the other hand, maybe I'll make a little separate comment here. If the population is already normally distributed, then n can be anything. So you can have n of 3, and it would still be a normal distribution for x bar. But it's saying, the central limit there and the power of it saying is that even if your original population was not normal, it's still going to give you a normal x bar distribution as long as your n is large enough. And of course, you might say, well, what does it need to be large enough? Like, what number is that actually going to be the case? And for us, we're just going to say as long as your n is at least 30. Now, who says 30? We just say it. It's just basically people have tried different scenarios, tried a whole bunch of different samples from different populations, and they noticed that around 30 is when things seem to work out better for almost every circumstance they came across. Now, it's not perfect, and if someone else told you we should really go to something other number, maybe 20 is enough, or maybe 35 is enough, depending on the context, I mean, I would go along with it. But for our class, we're just going to use 30 as our base case here. So let's do an example calculation. It says, suppose we take samples of size n equal to 25 from a normally distributed population with mu is 85 and sigma is 4. So because they tell us that the original population is normally distributed, then it's okay that my n is not at least 30. It's still going to work fine here. So if that's the case, then we now know that x bar is normally distributed. That means we're going to be able to use our normal CDF calculator in our calculator. And we know that the mean of x bar is the same as the mean of x is 85. Here's the part where some students make mistakes. The standard deviation of x bar is not just the 4 that I gave you. You have to take that and divide by the square root of n. So the standard deviation ends up becoming 0.8 here. So don't forget, when we are trying to find probabilities of x bar being bigger than or less than a number, that is when we need to divide by the square root of n here. So let's go ahead and we want x bar less than 86. Let's put this into our calculator. We know how to pull it up here on the normal CDF. So let's go here. Second, vars, normal CDF. We want everything less than 86, so negative infinity up to 86. My mean was 85, and my standard deviation was 0.8. And here's where the problem. If you had put 4 in there instead of 0.8, your answer is completely wrong. But by putting 0.8 in there, we get the correct answer of 0.8944, it looks like. 0.8944. 0.8944. So all we have to do is understand that it's going to be a normal distribution problem, figure out our new standard deviation, plug it all into the normal CDF function, and we get the answer that we are looking for.